going from the top towards the bottom, changing the orientation of the sockets. If the value is 1, however, I will have a tile that is not allowed to change configuration. This is useful when you are working with tiles that contain special patterns that should always be facing the same north direction, like a tile with flowers. For now, I'm gonna leave this at 0. If we move to the next one, and then the next one, we will eventually complete all of the different values that encode our metadata. Here is our example. Let's save this file and let's move to the implementation. With the metadata file safely stored within our folder system, sitting within a folder that contains the images and the different resolutions for those tiles, we can now go to the demonstration of this algorithm. Our program, as usual, is divided in 3 sections. In the module section, we're gonna need the Pygame library and the random library. In the data definitions, we will cover that information that represents hyperparameters, values that once selected cannot be modified during the execution of the program. The first one, and one of the most important ones, is gonna be the resolution. The resolution is represented within the folder with the same names within the folder name tiles. If I open the folder tiles, you will notice that there is a series of subfolders that contain a set of every single tile of reference with the resolution reduced or readjusted to the name of that folder. I'm going to start with the 16 resolution. The next element will be the dimensions. How many tiles we want per columns and per rows. This combination of parameters will give rise to the two-dimensional grid. Then we can include the dimensions of the screen. The screen is represented by taking the number of columns and multiplying it by the resolution. We are transforming number of tiles into number of pixels. And the same goes for the number of rows and the number of pixels per height. Now that we have the parameters of the screen, we can build an actual screen using the Pygame library, display sublibrary, and the setMode method, which receives as an input a tuple that will specify the dimensions of our screen. Then we're going to specify as a hyperparameter the name of the folder, which contains all of our tiles. In this case, it's called tiles2. We are going to specify a path where we are going to find the images. This one is a formatted version of a string that receives variables in Python and transforms them into their string versions. Here we want the name of the main folder tiles2, followed by the resolution that we selected, and from there we can find all of the different tiles of reference. We also need to specify the location of the metadata as a txt file. This is again a formatted string that contains the name of the main folder where we will find the tiles, followed by metadata.txt. Let's think about the basic unit of information in this program, that is a tile. But we can think about tiles as parallels. On one side we have the information represented as metadata, aka the tiles of reference, and on the other hand we have the actual tiles that will receive the identity of those template tiles. Let's start with the first one by designing the metadata. The metadata will be a list where every item is represented by a dictionary. It represents a collection of metadata for the tiles that can be used in the wave function collapse algorithm. Metadata will start as an empty list. The purpose here is to read the file and populate the list of metadata by creating dictionaries along the way. We do this with the context manager. With open, and we can specify the path to our metadata. We can specify that we want to read this file as read-only, and we're going to read it with the name file. File will be equal to itself, but a version that contains now a list of lines. For every line in that file, we are gonna first get rid of the backward slash, which represents the end of the line, and then we're gonna split each of the elements inside of that line by using a separator, which in our case is the backward slash t. We're gonna say line is equal to itself with a strip version, and once it gets stripped, we can split it. And we're gonna split it by using the separator tabulation. Here we will implement the evaluation step as to whether or not we are supposed to rotate our tiles. If the fifth element of each line, which is whether or not it's fixed, the binary value, is equal to the string 1, then the metadata entry for this particular item will be equal to a dictionary that contains an ID or name of the dictionary represented by the first element of that line. It will also contain sockets organized from the right in a clockwise direction, right, down, left, and up. We are going to have the line at index 1, line at index 2, 3, and 4. The next element we will add is represented by a boolean representing whether or not this item is fixed. However, if this element is not supposed to be fixed, the metadata entry will be equal to one of the 4 different rotations. This will be represented by running a loop variable a that will take the identity 0 to 3. Notice that fix in this case is going to be set to false, and we need to adjust the sockets to accommodate to the rotation in which we want this particular tile. So we're going to need to access a helper function called rotate sockets. That is going to take an iterable object, which in this case is our list, and it will return a version of the same type, a list of strings, but this time rotated. So let's create our function rotate sockets. And this is going to contain a list named sockets. Although the process seems a bit complicated, it's in reality rather simple. To demonstrate why, let's write down here a series of indexes representing the positions 0, 1, 2, and 3. Remember, the first element will always be the position on the right. So what does it mean for us to rotate something 90 degrees to the right? Well, it basically means that the element that is sitting at the top, or the up direction, which is the last element, will become the right direction. The current element in the right direction will become the down direction, and so on. So every element in the list is moving one step towards the right. This means that the previous element will become the new element taken from the left. For the first element, this would be coming from up. Then 0, then 1, then 2. So it seems that we also need to represent the particular angle of rotation that we want to apply to our sockets. 0 being no change at all, and 3 being 3/4 of our rotation, or 270 degrees. This is information that therefore has to be passed directly to the call of our helper function rotate sockets, and the value is going to be taken directly from the loop variable that we call a, where the purpose of this for loop is explicitly to provide the different rotations. Over here, the only thing we need to do is to return a new version of the list sockets with the rearrangement. We are going to use list comprehension for this. We start with the open and close square brackets, and we're going to specify that we want the element in the list sockets at the index I with a value of the angle subtracted from it. This relies on the use of a mathematical relationship known as the modulo, which Python automatically assigns. This means that if we are in the first element in the list, taking from the left, will simply mean taking from the last element on that same list. And then we need to do this for every element I in a range of values that represents the total number of elements that the list sockets have. Because we are working with squares, this value will always be 4. That is rotate sockets. Let's run this and let's see if we get any errors. The program opens briefly and it seems to be working. It's just that we don't have specified anything to render and we are not calling a loop in order to keep the window open. Let's scroll down and let's keep working on the meta entry. For each of these values of the meta entry, we also need to save the information that we generated in the form of a dictionary. That means that we need to call for the original list metadata, and we need to append to it the value of the entry that we just processed. Let's print out the first 10 elements inside of our metadata. Let's scroll this up, and here you can see what the values look like. You have the identity or name of a particular tile reference. You have then the different configuration and position of their sockets. And then you have the information as to whether or not this value is fixed. But there is one additional parameter we need to add to our dictionaries, and that is the information on the particular rotation that this particular tile reference has. Therefore, we're going to add it here as a rotation. In the case where the metadata is fixed, this value will always be 0. It is the original rotation. But what would be the value for the rotation for those cases when the metadata is not fixed? We use the angle A. And now we can proceed. That would be one of the units of information in this program. The next one would be the data definition tile. A tile will be the actual element or visualization that we will use to run our animations. And it represents a tile for the animation of wave function collapse in a two-dimensional grid. In theory, this implementation can be adjusted to n dimensions. Although computationally expensive, procedural generation is not restricted to 2 dimensions. This element tile would be a class that starts with the constructor that contains self as the instance of the class when a new object that belongs to this template is created, and then the value C and R representing the columns and the rows in which this particular tile lives. These values are constants. Once they are defined, they are not modified. This means that the tile doesn't change positions within the grid, and it always has the same neighbors. Self.c, a form of registering the variables within our constructor, will be equal to C, the parameter that we receive from outside when we create that tile. In the same way, cell.r will be equal to R. The coordinate or position of the top left corner of the square that represents this tile will be calculated based on the value in C multiplied by the resolution. The position in Y will be equal to cell.r times the resolution. Then we need to load an image. If you remember, when we were making the metadata in the txt file, I mentioned that there was an additional tile, a black one, and this is always going to be the element listed as the last item in the enumeration inside of our folders. We are going to load it and we're going to save it as the default value with which the program starts. We say pygame, load an image, following the path and adding a formatted version of the metadata at index -1. This will give us the last element in the list of metadata, which, because of the way we process this information, will always be the last element in the enumeration, and we want its name, which is its ID. Then we can call .png. If this is too confusing, something you can do is just going to your file system and finding what is the last element. In my case is 9.png, so this is the same as simply typing 9.png. The reason why I don't do it like this is because I want to automate the process. I would like to be able to add additional tiles without having to readjust the parameters in the program every time. I'll leave it to your criterion. Then we identified the rect component, which is the hitbox but also the area in which a rectangular object or a sprite is defined within the Pygame system. This will be equal to the image we already have, and we're going to extract the rect component out of it. This is a standard Pygame protocol. Then we need to specify that the position top left of that particular tile is going to be the coordinate where that tile lives. This will avoid the problem of rendering the tiles overlapping each other at the top left corner of the screen. Instead, we are asking the tiles to move an offset that is represented by their particular coordinate x and y. The next element will be attributes related to the wave function collapse. The first one is called the entropy, which means how many potential candidates we can use to assign to a particular tile. The lower the better. At the beginning, because the tiles have no identity and no neighbors that have been collapsed, they have every single potential tile as a candidate. Then we establish a new attribute called potential tiles. This will be a copy of the metadata that we already have, a list of dictionaries. This list will be curated every step in the loop, and hopefully the values will start getting smaller and smaller up to a point when we are ready to collapse this tile. The next attribute is a boolean that represents whether or not we have collapsed the tile. If we have collapsed the tile, then we don't need to run iterations anymore because we are certain. Then we calculate the sockets, and these ones will remain empty but populated with 4 elements at the beginning of the animation for each of the tiles. These are the values of the sockets when a function gets collapsed, and they will be populated only when we are ready to collapse that tile. Then we need to specify information about which neighbors we have. Self.writeNeighbor will be equal to a dictionary on its own, not to confuse with the metadata. This is simply positional information that tells us whether or not a neighbor that we may have to the right has been collapsed. At the beginning, we have no evidence, no information, so we don't make assumptions and leave it as none. Then, if the neighbor was collapsed, it is assumed that it already has a socket. At the beginning, we don't assume. We need another 3 neighbors, one for the right, down, left, and up. The next component will be the draw function that we can start with self. In this function, we simply call the display.bleed method that will receive an image and a particular position represented with the rect component on where to draw that particular image. That is the cell.rect. So let's talk about the implementation of the actual algorithm. Each of our tiles will have to update their neighbors. This means looking to the neighbor on the right, bottom, left, and up, and if those neighbors are collapsed, extracting the sockets Once we have evidence on the sockets, we can update the value of the entropy. This means calculating how many different sockets can fit this new configuration based on the neighbors we have around. The next step will be to traverse the entire two-dimensional grid and extracting the minimum entropy in the system, along with a list of candidate tiles that contain that value of entropy. Then we pick one of those and collapse it by randomly picking among the potential tiles. The next function we will need as part of the tile itself is called update entropy. The process receives a score on the lowest entropy in the entire system because it is a variable that gets updated for every single tile. But it is a global variable that exists for the entire system, not just for this tile. The tile contributes to the understanding of what that lowest entropy value is, and it helps us update it or return it intact. So here we're going to say a placeholder tile set, and it's going to be equal to an empty list. For every potential tile in the list of potential tiles, remember this is iterating over a list of dictionaries, we start with the assumption that this is a valid tile based on the understanding of this tile around its world. So the hypothesis is that this is a valid tile. If, however, the neighbor to the right is collapsed, that's the most important component, and it is not the case, then the socket of that particular neighbor matches this potential tile, then we turn this valid tile into false. We need to find a way to evaluate if a particular socket of this potential tile matches or not matches the particular socket of the neighbor, which is cell.right neighbor at the position socket. Remember, we are comparing dictionaries. So this has to enter a helper function. We're going to call that helper function socket match. And before we can jump into the implementation of the helper function, let's focus here on the particular index that we are going to access. The index will match the number of the index for a list that contains the 4 different directions that we specified before. In our case, because this is the right direction for the right neighbor, we're going to add a 0. At this point, there is a chance you may be wondering why we're using 0 and not the complement that corresponds to the opposite side. That would be the number 2 for the left direction, the adjacent side to the right neighbor, relative to this socket. And the reason why is because when we encode the information of the neighbor later in the implementation, that socket will already represent the complement. Let's implement the socket match function. This, being a helper function that is a global variable, will exist outside of the tile class. Let's call it socket match. And this is going to receive 2 strings that we will call the socket and the target socket. The general idea here is to compare opposite ends of the string. Let's take a look at this example here. Let's suppose that we have 2 squares, a tile on the left and a tile on the right, and the tile on the left has the sequence GGV, whereas the tile on the right has the sequence VVG. These 2 sockets match. However, the sequence for the tile on the left is GGB, whereas the sequence to the tile on the right is the inverse, BGG. What we do is to pick an index I that starts at 0, looking at one of these sequences. And then we look at the last element for that index when the index is 0, which in our case is the index -1. We update the index to 1 and we compare against -2. So we compare these 2 and then these 2. When the index is 2, we compare against the first element. So the value that we are looking for in the second sequence is the value of the original index I plus 1, and then we turn it negative. We can accomplish this by using a for loop that goes through every single index of a letter, and we can use enumerate to extract the particular identity of the item that belongs to that index. We start with the assumption that the two sockets match, and if we find at least one mismatch, that is enough to refute the hypothesis. We return false. If the socket at the position index letter is not the same to the target socket at the position negative index letter plus 1, then we return false. If, however, the for loop goes through every single item and we don't refute the hypothesis, we return true. That is the definition of the function socket match. Let's scroll back down. If the answer is yes and these two don't match, then valid tile becomes false. If at least one of the sides cannot be placed with this potential tile, we discard this potential tile to the final list, therefore reducing the entropy. We need to repeat this process, this time going through the down, left, and up neighbors. So here they are. Once we have finished going through the different cases for this particular potential tile compared against the neighbors, if we still have a valid tile, then we can set to the placeholder tile set the current potential tile. The tile of interest has passed the test and now it can move to the next round. Otherwise, at the end we set potential tiles equal to the placeholder tile set, therefore updating the list of potential tiles. So how do we calculate the entropy from here? The simplest thing to do would be to just count the total number of the candidate tiles. However, I like to focus on the concept of entropy to discriminate against every single potential tile by their name only once. In other words, I don't want to consider the rotations. So for every single tile in the list of potential tiles, I'm going to ask if I have seen this or this ID already. If the tile's ID, remember the tile is metadata, has not been seen in the seen tile list, we add to the seen tiles list the particular tile's ID. And finally, once we finish traversing this, the new value of the entropy will be equal to the length of that list. Now, if you remember, we had an additional parameter that was being passed to the update entropy function, lowest entropy. Here is where we're going to use the lowest entropy by asking if that current value of the lowest entropy is nothing, which means that this is the very first tile that we evaluate, or the current entropy is less than the lowest entropy found so far, it means that we have found a better candidate. So we return instead, as the lowest new entropy, the cell.entropy of this tile. If that's not the case, we simply returned the original value of the lowest entropy. So what about updating those neighbors? The process of updating the neighbors is also a helper function. Update neighbors takes self, and what it does is evaluating the 4 different cases, conditioned upon the existence of those neighbors relative to which tile we're looking for. If we're in the first tile, then there is no neighbors to the left. If we're in the last tile in the columns, there is no neighbors to the right. So we need to account for those cases. If this tile is not collapsed, first of all, otherwise it makes no sense to even evaluate these conditions, we're going to take as the value in C cell.c and as the value in R cell.r. And this is simply because I don't want to be writing cell.c and cell.r as indexes every time. You'll see why in just a second. And we're going to start with a simple question. If the number of columns is less than the total number of columns that I specified minus 1, it means that we are in the second last tile, which means that we can still look to the right. If we were in the last tile, we wouldn't be able to do so. So self.right neighbor is going to be equal and it's going to be equal to a dictionary that starts with collapsed, and it's going to take the identity of the object at this particular row and this particular column plus 1. The position C and R are the particular coordinates in the grid where this tile lives. By adding plus 1, we're looking at the item to the right. And then we're going to ask if this value is collapsed. We're simply going to pass it. If the value is collapsed, then we're going to look into the sockets that are on the right. Otherwise, we won't do anything. We take this element and we paste it over here. Now, we don't have a grid yet. We're going to make it in just a second. However, the grid is made out of tiles, so first we need to prototype that tile. Then we need to ask for a particular socket. Because we are looking at the right neighbor, it means that that right neighbor has, as the side that is adjacent to us, their left side. If our neighbor is to the right, that neighbor has its left side adjacent to us. So we are going to pick the index 2, right down left, 0, 1, 2, that is going to be the left neighbor. Let's move to the next condition. If the row is less than the dimensions at index 1 minus 1, we repeat the same process, this time adjusting for the down neighbor. We take the position at R plus 1, not C plus 1, and instead of the index 2, this neighbor has their upside facing towards us. So this would be the index 3. Let's move to the next condition. If C is bigger than 0, it means that we can still look to the neighbors to the left. That means we have left neighbors. We take grid at index R, C minus 1, in both cases, and the neighbor on the left is giving us the right side, so that's the index 0. And finally, when R is bigger than 0. I'm just gonna edit it real quick. And in this case, the neighbor that is above us is giving us their downside, which is the index 1. And you can see that we have the 4 indexes here, 0, 1, 2, and 3. That is updating neighbors. Now that we also have updating entropy, the last helper function we're going to implement is called collapse. This is an action that takes in consideration a particular potential tile and then just collapses by setting the entropy to 0 and acquiring the identity of that particular tile. We start by changing the parameter collapse from false to true. This is the only place where that happens. If the length of the potential tiles is bigger than 0, it means that we have at least one potential tile to pick from. So here we're going to say the potential tile equal to a random choice. This is the first time we pick random. That is going to take the list of potential tiles and simply assign it. Otherwise, if the list is not bigger than 0, that's a problem. It means that we didn't account for a special case or configuration where a tile had to be assigned. Here, the potential tile would be the default, which will be metadata at index -1. Regardless of what happens in the previous step, we'll make the name the potential tile at the current ID, and we're going to load the new image that we're going to read using the Pygame library. Using that name, we take the current path within a formatted string, and we look for the self.namefile.png. Keep in mind that naming your tiles numbers is what makes this line of code happen. Self.sockets will be equal to the potential tile at the index sockets. We, as a collapse tile, are acquiring the configuration of the sockets to give to our neighbors relative to the potential tile that we collapsed into. Then the entropy will be equal to 0. One of the last things we're going to do is to set the new image to be equal to the image of that potential tile. However, we need to also consider the rotation. So we set pygame.transform.rotate. And we're going to take as an input the previous surface, which is the image that we just loaded in line 115. And we're going to rotate for the potential style rotation. However, because of how Pygame works, moving to the right is actually going negative. So I'm going to need to add this negative value of rotation. And I need to multiply it for 90 degrees so that I turn straight angles. You can play with that parameter if you like, it's quite amusing. So that felt laborious and a bit intense, but that is the information that represents a tile. It seems that we have an error here as well. Let me find it. In ID. And this is a good teachable moment. So in line 52, I get the error that I get a wrong syntax. Python receives within its string format only one pair of double quotes. If I want to add more quotes, I need to make sure they are single, or vice versa. Okay, so now that we have the tile, let's create the grid. This will feel very similar to other tutorials, so I'm just going to go straight ahead. A grid is a two-dimensional array of tiles. The number of tiles is given by the number of dimensions at index 0. And we're going to make as many of those lists as necessary, as many as we specified in dimensions at index 1. It represents a two-dimensional array of tiles. The grid starts empty, and our purpose is to populate it using procedural programming. For every row in a range of values that goes from 0 to index at position 1, the number of rows, we create one empty row. For every column in a range of values that goes from 0 to the total number of columns at dimensions at index 0, we first generate a new tile that is gonna receive the position C and R, and then we append it to the row. We say row.append and we place the tile. Once we're done, we append to the grid. We append the row. That's it. Now we have a grid. The same grid that we used right here in line 100 all the way down to line 106. You can see it right here. Let's run this program and let's see if we get any errors. Good, no errors. The program runs and halts almost immediately. Now that the hardest part of our program is done, which is modeling the data, we can finally move into the coding section. Although here we jump into a gray area, I often like to think about what we just did as part of the data definitions. So here is where we finally implement the algorithm. We start simple. We take one of the elements in the grid, which is a tile in the system, and we collapse it. We can ask it to now take an identity. Remember, this process is random. It can take any potential tile that it wants. Then we create a draw function that is going to take the surface that we created and is going to change its background color. Let's pick this color right here. If our program and our grid is produced properly, we shouldn't see any background color at all, because every pixel will be covered by our tiles. Here we need to use our template. Our grid is a compound data type of type list, so we use a for loop. For every row in the grid, we do whatever we want to do, but we do it to a row. A row is also a list, so we also use a for loop to iterate over every single tile inside of that row. And for each of those, we do whatever we want, but we do it to a tile. I'm going to copy the template and you'll see we're going to use it quite a lot. I'm going to fix the indentations, get rid of the comments, and here we are. So this part I am not going to use in this implementation. This one is a reference to my template for when I need to use higher order functions. But in this case, I don't need to. So the first thing I'm going to do in my algorithm is to update my neighbors. So I can say tile.update neighbors. And we add the brackets. The function update neighbors is in charge of evaluating which neighbors we have, if they are collapsed, and if they are, to assign their sockets. Once I am done assigning the neighbors, it's time to calculate the lowest entropy, this time a global parameter, that starts at none. Not 0, but none, because if I use 0, then no matter what value of entropy the lowest tile has, it will never be smaller than 0. And I repeat the process. I paste my template, add indentations, fix them. I don't need this again. And now, if the tile is not collapsed, otherwise it doesn't make sense to evaluate the entropy, then I can set the lowest entropy, which is the return of the method update entropy of the tile, to be equal to the tile.update entropy. And to this function, remember, let's see the template, I need to pass the lowest entropy. So let's pass it over here. So lowest entropy enters, lowest entropy exits, with the old or an updated smaller version. Lowest entropy will calculate also which are the new potential tiles that this tile can take, based on the number of neighbors. Once we are done, we can get a list of candidates. A list of candidates represents those tiles that will enter the next round when picking the next tiles to collapse. I paste the template once more, get rid of the comments, fix the indentations. Here I can ask again, if the tile is not collapsed and the tile's entropy is also equal to the lowest entropy, it means that this is a candidate. So I add this tile to the list of candidates. And finally, I need to ask, if there is at least one candidate in the list of candidates, it's time to collapse another tile. So I take the list of candidates, and here I can pick at random. I can pick the last element in the list, I can pick the first element in the list, and it will yield a slightly different result. But for now, I'm just going to take the first element in that list and I'm going to collapse it. And the program is done. Notice how once we establish the helper functions that we required, processing it was extremely simple. And here, one of the important things is that draw function should only be in charge of rendering images. So actually what I'm going to do is to put this piece of code into a second function called update. And here I'm going to repeat the process of going through my two-dimensional grid using the templates. And what I'm going to do is to call the draw function. Once I'm finished, I'm going to ask for the handshake that Pygame does with another programming language, which is the one that actually renders the screens, which is one of the family of C languages. Now we have a draw and an update function. So let's run this using an infinite loop and let's see what happens. Forever, draw, and update. Let's run this and let's see what we get. Excellent, the algorithm works. But there is a tiny little bit of a problem. If I click on the window and I try to move it around to show it to my friends, the function collapses. And the reason why this happens is because our window is not interactive. To make it interactive, we need to add a small addendum to our update function. We say that for every event in the list of events of Pygame, if the event is of type quit, which is a constant parameter that the Pygame library has that is represented as the boolean of whether or not we are closing the window. We exit Pygame. This has the nice side effect of making our windows interactive. And this time I can just move the tiles around. Now this tile set is quite interesting, I really like it, but I have another one that you are also gonna find in the GitHub page that is attached to this video tutorial. Let me close it and let me show it to you. You may have wondered why the name of the tiles folder was tiles2, and it is because it was the second example that I prepared for this demo. However, there is a previous generation called tiles1, or simply tiles, that look like this. They are tiles inspired from an RPG tile set that I found online, so I separated them into their different components and used the same principles that dictated the previous implementation. So now that I have it, in theory, if I change these from tiles2 to tiles, and knowing that the metadata file is located within the tile section, let me show it to you, it's right there. If I run the program, I would expect to see the updating of this procedural world. I'm going to leave it running for a bit and I'll show you the final result. And here it is. A good example on procedural landmass generation. Let's think a bit about how we can export this information and use it somewhere else. Each of your tiles preserves the metadata that it inherited. That means that you can traverse the two-dimensional array and export the identity of each of your new tiles in the form of a TXT document that you can read in other programming languages or engines and use it to extend this algorithm to a quote-unquote three-dimensional landscape. But besides that, you can also assign special attributes to each of your tiles. Like for example, everything that is ground could be considered to be a path where the character can move.